Okay, cool. Thank you. Thank you for joining the Tech Talk today. So today my talk will be really focusing on like SaaS, and I think my topic will be like trying to give a perspective and why you should build a SaaS application using TIDB from day one. So my view of SaaS maybe is really like spreadsheet. So when I like thinking about SaaS, really like some advanced version of Thread. So that's why I put the kind of the figure here. And if you think about spreadsheet, it has a few features. You can integrate with the different data sources, so you can create different views of your data spreadsheet. And then nowadays, from Excel to like SaaS, I think the difference is that it used to run on your own machine, deployed on your laptop, on your server. Now is hosted on the web, on the cloud, and the manual users can access data. You can share your data with other people within your organization or outside your organization. So that's basically my view of SaaS. It's really like old stuff, but has a lot of innovations in the cloud era. So here are some of my background, and thank you, Chen Hao, for the introduction. And from my part, really, I think I'll take this joke again. So prior to joining PingCAP, I've never used any relational database in my past career. Even MySQL, even like Postgres. My work really mainly on focusing on MySQL and focusing on stream processing using Kafka and Spark. So my previous experience is focusing on the big data part and the fast data part. And now I think after working here about 3 years at PingCAP, I can say I know a little bit about databases. And I think database is such an amazing topic. And each day I work on it, I feel, oh, it's really an interesting topic. And it really, I can feel and see the beauty and challenges of building databases. So before I talk about that, I want to quickly introduce TIDB a little bit. I believe many people may not hear about TIDB before. And what is TIDB? So TIDB is a distributed SQL. And I think one benefit of TIDB is that although it's distributed and from the user's perspective, it still acts as a single instance database. And MySQL, TIDB is MySQL compatible, and you can actually use MySQL client to talk to TIDB, and your application can use those ORMs that are built for MySQL to kind of like to work with TIDB. And it is highly available because it's distributed. It has replication and transactions built into the database. So it's highly available. And from the user perspective, if there anything fails for a certain transaction, you can just safely retry because TIDB supports transaction. And then TIDB is open source from day one and is cloud agnostic. It can be deployed on bare metal virtual machines on Kubernetes, and it can be deployed on different cloud providers. It's not a fork, it's not a middleware, it's also not a SQL Hadoop. So we build a database from scratch, and we are using Go and Rust. So when to use TIDB? So TIDB is built as a primary database, especially for scalable applications. And TIDB is especially good for SaaS backend and payment system backend. The other thing is, I think is also more or less related to SaaS, is that TIDB is good for data-intensive applications. It's for those applications that provide the analytical capabilities to the end user. Instead of like provide those analytical capabilities to the internal user, it actually provides those capabilities to the end user. So before I go, I want to do a quick demo, and this demo actually is a CRM. I think SaaS start with the CRM, start with the Salesforce. So on the left-hand side is this is kind of like open source CRM, and we made some like demo on top of it. So on the left-hand side is really the CRM running on MySQL, and on the right side is really on like TIDB. I think if you look at this video, I think one thing I feel that the kind of like the display of those graphs and dashboard is much faster on the right compared with on the left. So on the right is TIDB. So I think here I want to say that this is a bit like the SaaS workload. I'll talk a little bit more formally in the following slide, but it's really like for the SaaS workload, it's really like you work with different data sources, either by manually enter it or by integrated with the other data sources. For example, like Salesforce, for example, like the other data source. So you often want to create different views of the data. For example, here you have different dashboard, and also want to provide potentially ad hoc queries capability to the end user, because you want those queries to be served. Because, for example, if you're a sales manager running on Salesforce, you want to understand the deals progression. You want to understand the performance of your reps, and those kind of like queries will be ad hoc, and you want those queries to be returned within like the sub-second, so that you can see really like interactive like experience. So that's basically SaaS, and again, TIDB is much faster than MySQL for this kind of workload, and I'll explain why by walking through your some basics of TIDB's architecture and design. So, what is SaaS? So I mentioned a little bit a couple of times already in my talk. It's really like a spreadsheet. When I think about SaaS, there's a lot of SaaS really like advanced version of spreadsheet, providing easy to use template, providing easy to use tools for you to create workflows, and that's why I call it SaaS. And the other feature is that those applications are delivered on the cloud, and from the SaaS provider's perspective, it's really a multi-tenant application they have to build, and they have to make them like highly available, things like that. So one example is really Airtable. And here's what I take from the Airtable. And Airtable is your organization's single source of truth. It is how your teams and data and workflows are deeply connected by apps anyone can build, which is to say that this Airtable is built trying to integrate data source from different places, and then allow different users to modify the data, and then create automations around those data. So that is what Airtable does. And if you go to Airtable's like website, you can see there are a lot of solutions built for different verticals. For example, they will tell you how you can use Airtable to do project management. You can use Airtable to do CRM, and then how you can use Airtable to do marketing analysis and finance, etc. So that's really like basically there's a lot of like data intensive SaaS. If you think about like there are many verticals, likely special purpose built SaaS applications for different verticals. For example, if you look at CRM, there's Salesforce, and there's a lot of customer success platforms like Catalyst and Gainsight, and there's a lot of like know your customer type of like services available for fintech companies to build their applications. They are called Alloy and Persona, and there's a lot of kind of API services for you to build applications. For example, Nylas for communication data, and Twilio for working with cell phones and kind of like the service providers. That's a lot of them. So let's take a step back and think about what are those functional requirements if you want to build such application. I think the first thing I want to say is a collaboration. You want multiple people to be able to access the tool and modify the data. And the second thing, the data is the key here, because I call it the data intensive SaaS. So they need to provide capabilities to easily integrate data from different data sources, or easy ways for them to produce those data or generate those data. For example, they can integrate data from Salesforce, Jira, Zendesk, and maybe your favorite product management tools. And then they need to provide multiple views, for example, time-bound views, grid views for different users. And then they also need to query the data, and the data can be an arbitrary field because you don't know. You may want to explore data and figure out some insights from the data on the fly. And that query can be very ad hoc. It can be sales like performance, it can be other things. Also, the other thing is that those data models will change over time, and those data models can be different for different tenants. For example, in your Salesforce, your way of tracking deals may have different set of fields and other organization may not care about. and other organization may have another set of fields they may not care about. So those data models will change and they will be different by different tenants. Yeah. So those are some of the functional requirements. And then there are also a lot of non-functional requirements because essentially it is a SaaS and people choose SaaS for a reason. It has to be better than they manage by their own. So they want the SaaS to be highly available. It needs to have availability full nice or even higher. And from the performance perspective, they want to have the interactive like web application like experience to the user. So they want sub-second latency or even lower. And then this system needs to be scalable because you need to handle 1,000 to 100,000 tenants, and each tenant can have hundreds and thousands of users, even more users. So at the end of the day, from this system perspective, it's like a lot of users. They are trying to access the service, and the service need to be highly available. And those a lot of service users may issue ad hoc queries to the system, and periodically there will be data ingestions and data modifications. And the goal is that you want to make sure that those user experiences like a sub-second latency, it's like interactive experience. So that if you're a SaaS provider, you want to build such a system like that. And that is the experience you want to provide to your user. Yeah, so this is the user experience, but from the SaaS provider experience perspective, they want to make money eventually. So that may take a couple of years. So, but really from their perspective, they want a lot of small customers that is very low touch, and they also want to have many big customers, which they want high touch. And many small customers is a good kind of story for the growth, and the many big customers is kind of the base camp for their business. And they want efficiency. They don't want, if you acquire a customer, your cost of support infra will grow linearly. So ideally, even you have like tens of thousands or millions of customers, your maintenance cost or infra cost will stay the same as the number of customer grows. So that is what the SaaS provider wants. So at the end of the day, they need to choose a multi-tenant architecture. And they also want the infrastructure to be able to easily onboard large customers. They want to be easily build new data integration, because those are the key kind of like to their value to their customers and the key to their business success. So really, they need to consider a lot of things. So also, I want to say that those SaaS have a very interesting 80-20 rule of power law distribution from the data science perspective. Really, like I have worked with some of our SaaS customers, and my first-hand experience is like there's many small customers. Oh, sorry. There are a few large customers that occupy the majority of your data and the majority of your workload. And there are many small customers that may only consume a lot of a small portion of your resources. And the challenge with SaaS is not only about the 20-80 rule, it's also about the unpredictability of which tenant will become large over time. And then and those things you need to prepare for that. So in summary, if you look at the database workload for SaaS, is that they have a relatively large work set. If you are familiar with the database, work set is really how much data is charged by a certain query. And a lot of single node databases are built on the assumption that the majority of work set needs to be in memory so that they can be efficient. But for SaaS, because you have a lot of tenants, and they essentially access different data, and then the work set can be large because at the time they actually access different data, and that's actually not good fit for single node database because they can easily go over the memory limit because those are random access across different portion of your entire data space. And then they need the complex queries like joins and aggregations. And if you remember the demo, you'll see there's a lot of graphs. And there's also ad hoc queries, and those are basically computing some aggregations that are the KPIs, or perform some order by or like a group by things. And those are really complex queries and usually not easily kind of fulfilled by a single node database. And then there's practically data import and synchronization, which cause a lot of like load on the database. And there's frequent schema change, as I mentioned, your fields will change. You will want to add a new field you care about. You may want to add a new data source you care about. So from the database perspective, there can be frequent schema changes. And if you want to compound this with the number of tenants in your system, it's like you probably will see constant, always like schema change in your system. So that is a workload you have. And what is a typical architecture to build a SaaS backend? So I think the key here is really the metadata server and the database server. And the metadata server stores information about tenants, information about your billing information. It's really about the user. And the database stores the actual user data. So there are two layers. The metadata about tenants and database for the actual user data. And you can use NoSQL or relational database to build. But essentially, because SaaS is actually evolved from traditional enterprise application, and I think SQL database is usually recommended because that's much easier. It's much easier to use SQL to express your business logic versus you have to write your business logic using a single device interface and the code. That's much harder to maintain. We can take a little bit deeper, right? As I mentioned, so if you decide to use SQL to let's say build your SaaS backend, and there are metadata server and there are database server, and the metadata server is usually called the control plane, and that includes those administration services and the application side, which include the user data, and then the actual services of manipulating those data. So from the tenant distribution perspective, we can have some dedicated, like MySQL for some large tenant, and you can also have a shared tier, including small tenants. And then from the control plane perspective, you can have like a database for different like microservices, like billing, tenant information, and objects definition. So those are the typical architecture if you choose use sharding or you choose to use that single node database to build such application. But there are a lot of challenges with this, and these are actually kind of a summary from the real customer conversations. It's not something I make it up. So basically adding new functionality, if you take this architecture, will take a lot of time. So simply because you are using a sharded application, sharded database, and and when if you do any kind of like functionalities, you actually has to aware the database sharded. And sometimes the sharding key may not meet your needs. And one good example here is actually Slack, right? When Slack, probably many people has used Slack, and Slack has a feature called Slack Connect, and that allows users to, from two different organizations, to have a shared channel, and they can communicate with each other. And on each side, they can add people to the channel. And when they try to launch this feature, they have to reshare their database from the user to the channel in order to handle some of the to combine it from the limitations of the sharding. That takes a couple months, and this is not really adding too much value to the business. And it'd be good that they don't have to spend time on the resharding of the database when they want to add a new functionality like the Slack Connect. Also, I have to talk with many customers, and they're also concerned about, they're not very confident when they try to onboard some of their large customers. For example, this is the feedback from the customer success platform and some of the collaboration tools like Airtable. Their sales work very hard, sign some deals, but from the engineering side and the customer side, they are not really confident why they're onboarding some large customers, whether their system can sustain that. Mainly because of the capacity planning thing, right? So you don't know whether this database service has enough capability to handle the workload. Yeah. And oftentimes you have to move a tenant for various reasons. And one reason that you want to move a tenant is that the tenant becomes bigger, and this causes a lot of issues to the other tenants on the same database instance. And then that can be painful because now you have to work with the independent running database system. And this moving is very, very painful. It needs to be carefully planned and usually involves downtime. So this caused a lot of pressure on the SRE team maintaining the SaaS application. And the first one is often seen by our customers. If you use sharding, but essentially each shard is still served by a single node database. And the happy or problem for that is that some tenants really become big and it cannot be handled by any single database instance. And then they have to shard the database to manage one customer. And this also will need to change. They need to change their logic in order to make sure that each tenant can have multiple database instances, which is a pain in the butt. So those are the pain points if you use sharding. I think here the problem is that sharding eliminates a lot of capabilities that the database provides, and each shard is still a single node database. And then moving things around different independently running databases is painful and is often involves downtime. And then I think here's what I recommend. Using TIDB, you can eliminate all the pain points I just mentioned, and I'll explain why kind of in the following slides by talking a little bit about some of the design decisions and architecture of TIDB. So this is a TIDB architecture. And from the user perspective, it is like MySQL. You can use MySQL client to connect to it. And those TIDB servers are really like the multi-primary architecture, and each TIDB server can receive reads and writes. And this is different from the other kind of scalable database like Aurora, which is like a single writer, but for TIDB, it's really a multi-write, and each server can take the write and the reads. And from this design, both read and write will be scalable in the TIDB deployment. And on the storage side, we have two types of storage. One is the row store, and we call it TIDB, and the other is column store, and we call it TIFlash. So the data in the row store and data in the column store will be kept in sync, and they are strongly consistent during read time. So I will explain a little bit more in the following slides. But I think the nice thing about it is that I think if people are familiar with analytical database, and analytical database usually designed to be used column store, and column store really good for scans of some of the fields over a large range of data. So that is what column is good for. And TIDB is like row store. And TIDB actually support global secondary indexes on top of TIDB. And then as a result, any queries can take advantage of both rows and the column store if they see fit. For example, if there's aggregation, then it will go through the column store, and then there's the kind of point get or index scan or short range scan that can be fulfilled by index that will go through the row store. So that is basically why TIDB can be good for both the kind of transactional queries as well as more complex queries like joins and aggregations. And then TIDB has a component called placement driver, and the goal of placement driver is try to do failure detection and as well as moving data as needed. When you add a new node to the cluster, then the place driver will figure out, try to move some data to do some load balancing. And then when there's a failure, placement driver will also help try to handle the failover and try to create data replicas in the remaining nodes. So this is basically the TIDB's architecture. So in the next few slides, I'll talk about how TIDB achieves the kind of auto sharding as well as the global secondary indexes. So the data in TIDB is actually stored as key value pairs in TIDB. So if you look at those tables, and those tables will be represented as the key value pairs with the table information encoded in the key and of the table encoding the value. And for example, for any table, we'll have a T prefix with the table ID and the row R prefix with the row ID. And the data in TIDB will be ordered by the key using the lexical graphical order or the dictionary order. And we do the same thing for the indexes. So index is represented similarly as key value pairs, but using a different set of encoding. For example, if you have a secondary index, there will be prefix and T with the table ID and then I with the index ID. Then with the column you choose to be the index will be encoded in the key or in the key and pointed to the row ID. Or if the index is unique, if it's non-unique, the row ID will also be encoded in the key. And the goal is that, so both indexes and data are key value pairs. And yeah, that is kind of the idea. So if it look at the example, this is the simple user table, it will have a key, basically index and the name, and has a primary key and the ID. Then from the logical view, it will be like the fields. And then from the physical view, from the data encoding in TIDB will be like T and the table ID and then R and the row ID and then the column, then the values will be encoded in the value in the sorry, then columns will be concatenated and encoded as value in the key value pair. And similarly with the indexes. So this will be the infer, which is actually the name field in the user table, and that's actually encoded in the key. Because it's not a unique index, and then the row ID will also be encoded in the key. So that is how the data index is encoded in TIDB. And then one interesting fact is that because TIDB is essentially a very large dictionary or very large map, and then we actually divide those map into fixed chunk of regions, or fixed chunks of data space, and each region is like 96 megabytes, and they are ordered by the key. So, and the region will be the union of data placement and data movement. And in this case, so we have a region 1, 2, and 3, and each representing a key ranges in the key value map. And then PD will decide where to put those range or region into the storage node. And we use a protocol called Raft to ensure different copy data of the same region will be strongly consistent. And the Raft is current-based consensus algorithm. So this is another view of the data within TIDB or within TIDB. And these are different regions on the TIDB nodes. And those regions contain the information of the key value pairs, and the key value pairs are encoded according to the table encoding or the index encoding. So you can see the region 1, basically a table encoding, and they are ordered by those keys, and these are the code encodings for the index. They are ordered also by the keys, and those will be spread across different TIDB nodes. So that's basically how the data is organized there. And this is have a very nice property because of the data is distributed, and the user don't need to be aware of that. And also they don't need to be aware of data index is distributed. So when you do query executions, you can actually try to push down those computations to TIDB to do parallel kind of processing, because the data is actually scattered, or the index also scattered in different nodes, and you can push down the parallel processing to speed up the queries. And as I mentioned, the SaaS workload has a lot of joint aggregations, and the TIDB has the capability to push down those joint aggregations to TIDB and TIFlash to speed up those computation. You can utilize multiple machines and multiple to process those queries. And that's the magic behind you can return the complex queries, the user-facing complex queries within sub-seconds. And I also mentioned that TIDB has two types of storage. One is the row storage, and the other is column storage, and they are in sync. And from the TIDB perspective, they will decide where to read data from depending on query. And this is purely automatic and transparent to the user. Okay, so here are kind of like some magic behind the TIDB that make TIDB a good fit for the SaaS workload. And here I will give you a real world use case of a CRM SaaS provider that adopts TIDB. And this is kind of like a large kind of like a CRM. It has over 150K thousands, and each of them generate a lot of data and maybe tens of millions of rows in a single table. And then each tenant actually can be thousands of users that they can use it at the same time. So from this overall system perspective, there can be like thousands or to tens of thousands to hundreds of thousands of QPS queries per second on the system. So and also those queries can really be like ad hoc. For example, some of their use cases, including like their customer success people, when they receive some complaints online, they need to look through the some of the records or some of the history of this customer engagement. And this is very high up query, and they want this to be show up instantly so that they can help this customer. If it's slow, when you make a call, the customer will be unhappy if the query only return the result within the. You really like have a control of users. So because of that queries, and there's a lot of fields, you cannot really create an index on all the fields. And you really want the result to be returned within a reasonable amount of time, ideally sub-seconds, without any indexes. So that is one thing they need to support. And the other thing that there are SaaS, there are many customers. Many customers will add columns, change their data definition, remove columns on constant basis. And you don't want those operations to block the changes on you may make modifications of the data. So you would really need a non-blocking DDL, which means that when you do DDL, there's no impact on your DMLs, which are the kind of operations modifying the database. So basically, this is then they decide to evaluate TIDB, and when they start like with where they have the most pain points. They start with some of their large customers, which is already reached their like approach their limitation or the limits of their single node database, and those are good candidates for when you start building an application. So they evaluated TIDB and they did the migration. There's no downtime during the migration, and after that, they actually can provide those near real-time experience for the users if they run ad hoc queries. For example, here are like a few examples. One is ad hoc query on non-index data. As I mentioned, those are very much needed because this is to support ad hoc query for many users on 500,000 rows, and then used to be over 10 seconds. Now it's less than 1 second. Similarly with another ad hoc query. So the reason they choose TIDB is that TIDB offers out-of-the-box user experience, and they provide sub-second latency for the end user. And it is horizontally scalable, as I mentioned. All the information about data distribution, secondary index, and the distribution of secondary index are transparent to the user. And then user only needs to understand it's a table. And the only difference is that this table can store billions of rows without any issues. And underlying, you don't only need to add new nodes or new hardware or more hardware to support more data and to handle more like the QPS. So it's very easily. It's not like sharding. When you add new resources, there's manual data movement needed. And from the application perspective, application need to understand that data is distributed. It's a very different user experience. And TIDB support online DDL. And I think in the last meetup, we talked about that. This is really cool. And when you make changes to a schema, you can still run your applications, and the new schema will be automatically packed up when the DDL operation finishes. Also, TIDB is one database for both RTP workload as well as support some of the complex queries. And this can offload some of your cost or the need to use the data warehouse. Okay, so this is the final slide, and this is what I want to talk about. So if you are building a new SaaS application, consider using TIDB from day one, because if you use TIDB, that will eliminate most of the pain points. As I mentioned, for example, onboarding lots of customers, for example, launch a new functionality that your original sharding key cannot meet your needs, and then migrate some tenants to another shard. And then if some of the tenants become large, you can still like continue to serve with the same database without like sharding again, or end up with no solution, right? So if you already build your such application with sharding or NoSQL, and I think there are a few opportunities for you to migrate TIDB to reduce your pain points and to further support your business growth. For example, you can start with database for large tenants, and those are typically good candidates. And then also TIDB is good fit for shared tenants because that essentially can also be a lot of users there. And also your metadata or control plane is also a good candidate for TIDB because those tables are usually not sharded, and is typically served with a single node database. But as you onboard more and more customers, that can be the bottleneck for the system. And those are also good places for you to start, kind of like using TIDB. So that's under my talk. I think the really information I want to convey is that I think with the technology advancement for the past couple of years, I think the distributed SQL is already become mature. And I think the nice thing about it with distributed SQL, the users still only need to think about database as they did with the single node database. And this is very valuable. So for those distributed SQL databases, they can be scalable and they can offer features like unlock DDL to really ease the maintenance and operation of the SaaS application. Yeah, that's all I want to share. Thank you.